Very few experienced anglers need to rely on the critical features listed in the identification guide. Most experienced anglers know immediately what kind of fish they have caught. They can identify the difference between a brown trout and a rainbow trout because they know what the brown trout looks like. They know where it is going to be found. They know when they are likely to catch one species or the other. All of this information allows the expert to quickly identify a subspecies, whereas the novice will take longer, may have to use diagnostic rules, and may even have to consult a guide. In short, the expert's identification is fast, effortless, and memory-driven, whereas the novice's identification is slower, more laborious, and rule-driven. This kind of expert-level perception has been studied more systematically in the area of bird recognition and fish identification. Bird watching, birding, is a hobby and recreational pastime that is enjoyed by many people with different levels of expertise. I am not an experienced birder. I can identify a few birds by sight, but for the most part I group birds into several very big and broadly defined categories: small birds in the backyard, hawks and birds of prey, water birds, birds that are sometimes eaten by people. This is a very coarse description and not an expert-level analysis, but I know several people who are expert birders. People who engage in birding as a hobby often look to acquire a list of all the different kinds of birds they have identified. This is referred to as a life list. As a result, they spend a lot of time looking at birds, identifying them, and classifying them. An interesting study by Johnson and Mervis, 1997, looked at how experts differ from novices in terms of identification and attribute generation for species that were within their range of expertise. Their participants included a range of experienced and intermediate bird and fish identification experts from biology departments, the Audubon Society, local aquariums, etc., as well as university undergraduates who were not experts in either field. In several experiments, participants were asked to identify pictures, generate exemplars and attributes when given a category name, and identify silhouettes of birds and fish. Although it was expected that experts would generate more responses, what was interesting was that the experts seemed to show a preference for responding at the subordinate level. That is, whereas novices generated more names and more attributes at the basic level, experts demonstrated that their preferred level of identification and classification was at the subordinate level. In other words, experts seemed to show a basic level category advantage within their level of expertise for objects or animals at the subordinate level. Whereas most people intuitively name objects at the basic level, see Chapter 4 for a description of the basic level, experts do the same thing but at the subordinate level. Medical experts also show expertise-related perceptual advantages. In an early study by Lesgold and colleagues, 1981, novice, residents, and experienced radiologists were shown pictures of an X-ray and were asked to identify anomalies and generate a think aloud protocol as they did so. Not surprisingly, experts were quicker to notice the anomalies. The more interesting aspect of the study was the result that experts were able to describe far more basic anatomy in the X-ray compared to novice participants. This implies experts will spend less time on the surface characteristics of the image and be better able to notice the anomalies. In other words, these experts had a considerable store of previously seen images of lung X-rays and so did not need much time to process the basic anatomy. They can essentially fill in the details from memory. In general, this work on expertise and perceptual identification suggests a conceptual advantage for experts that helps to drive the perceptual identification advantage. Experts have a richer conceptual structure and better differentiated concepts. This allows the expert to fill in general, category-level detail from memory so that they can process features and make identifications at more precise, subordinate levels. The suggestion that these identification advantages are a result of experts' conceptual structure prompts an investigation into expert advantages in classification and expert-novice differences in similarity judgments. Similarity. Chapter 2 discussed the psychology of similarity. One of the things that I mentioned was that experts are more likely to be able to appreciate similarity in terms of deep features than surface features. As an example of the difference between these two kinds of features, consider three simple objects: a red apple, a green apple, and a red rubber ball that is the same size as the apples. You might identify the red apple as either a gala apple or a red delicious apple, or something similar. You might identify the green apple as something like a Granny Smith apple, and the red rubber ball would be like something you would use to play handball. Now imagine that these three stimuli are arranged in a forced choice classification task. This task was described in Chapter 2 in the section on assessing similarity. In this case, the red apple is the target, and you have to choose which is more similar, the green apple or the red ball. On the surface, the target stimulus is more similar to the red ball than it is to the green apple. They are the same size, they are the same color, and they are the same shape. However, most of us would rate the similarity between the target apple and the green apple as being higher. Although they are not the same color, they are the same size and shape, but more importantly, they share deep feature similarity. They are the same on the inside. They belong to the same class or category. Because we have experience with apples and balls, we recognize this as being the stronger pairing. A completely naive subject, or a computer with sparse semantics, might still choose the apple and ball comparison on the basis of surface features. In general, the literature has supported the conclusion that experts are better able to perceive and use deep features when compared to novices. An influential paper by Ch et al. 1981 explored the interaction between expertise, problem solving, and similarity. They noticed that some existing literature suggested experts can quickly classify and categorize problems on the basis of solution-relevant features. For example, they noted that university students can categorize algebra word problems into types and categories, and this classification occurs very quickly. The implication is that upon reading the problem, a student with experience can perceive the deeper structure of the problem. To investigate this idea within the context of professional expertise, Ch et al. Studied the ability of physics experts and novices to quickly classify physics problems. In order to classify and group problems, it is necessary for the classifier to make a judgment about how similar one problem is to other problems. If experts are better able to perceive and use deep features, then they should group problems together on the basis of deep, solution-relevant features, whereas novices should group problems together on the basis of surface features. Their initial study utilized a sorting procedure. They contacted several advanced PhD students from the physics department at Carnegie Mellon University and several undergraduates who had minimal experience with physics, having studied one course in introductory physics. Because of the amount of time spent on studying physics, the assumption was made that the advanced PhD students were considered experts, although keep in mind that these physics PhD students would not be considered experts according to Erickson's definition that was set out at the beginning of this chapter. The participants were then given 24 problems that came from a standard textbook on the fundamentals of physics. Participants were instructed to sort the problems into groups based on similarities of the solution. They were not allowed to use any writing material and were not asked to actually solve the problem. Figure 11.4 Examples of grouping of physics problems by novice and expert participants. The figure shows the results from Ch et al. 1981. The boxes around problem 7 were added for this figure to highlight that they are the same problem. Examples of physics problems, so they're sorted differently. Figure 11.4 shows an example of several of the problems they used. The panel on the left shows a grouping by novices. Novices grouped problem 10 and 11 together because both showed a disk with some velocity. Novices mentioned things like angular velocity, momentum, circular things as justifications for their grouping. Novices also grouped together problems 7.23 and 7.35, which showed blocks on an inclined plane, and mentioned things like these deal with blocks on an inclined plane as a justification. In the panel on the right are some groupings made by experts. Notice that the experts put together problem 621 and problem 735. On the surface, these problems look very different. Furthermore, notice that problem 735 was grouped with inclined planes by the novices but not by the experts. The experts seem to rely on the basic principles of physics that are involved in solving the problem in order to make their grouping. One expert says, work energy theorem. These are all straightforward problems. What this means is that novices, although they may be able to solve the problems, group them together on the basis of how the problems look on the surface. Experts are able to ignore the surface characteristics and group the problems together based on a conceptual, deep understanding of how the problems would be solved. Other studies in the same paper replicated and confirmed this finding. For example, one study asked participants to elaborate on their problem-solving schemas. As expected, novice schemas were relatively sparse and emphasized surface features, things like blocks, planes, length, etc. In contrast, representations of expert schemas included principles of motion, conservation of energy, Newtonian laws, etc. Taken together, Ch et al.'s 1981 study reinforced the notion of expert-level advantages in similarity and the influence of expert conceptual structure on problem solving. More importantly, this paper set the stage for much of the modern work on expertise in professional domains. Classification. The relationship among similarity, classification, and expertise was explored in even more depth in a fascinating paper by Doug Medin and colleagues, 1997. We discussed this paper briefly in Chapter 6 when discussing how people make inferences and inductions about concepts that they are familiar with. In this chapter, I want to emphasize the role of expertise. Building on Ch et al.'s 1981 demonstration of experts' tendency to perceive and use deep, solution-relevant features in their sorting and classification, Medin et al. 1997 reasoned that subtle differences between types of expert should result in differences in the way in which experts classify at subordinate levels. In other words, they speculated that experts form categories on the basis of goals that are relevant to their individual expertise. Medin et al. Examined the classification and reasoning abilities of three kinds of experts with trees. The first group were landscape designers, architects. These were individuals who worked with clients and municipalities to design and plan landscapes. They need to be experts in trees and to know what kind of trees to plant in different circumstances and scenarios. They need to know what kind of trees were likely to require additional maintenance. They need to know how fast trees grow and whether or not they would create additional landscape waste, like a black walnut tree that drops walnuts all over the ground. A second group of experts were municipal park maintenance workers. These were professional arborists employed by the city to look after and tend the many trees on city property. This study was carried out in Evanston, Illinois, and between Evanston and Chicago, there are an enormous number of parks and old trees. These experts need to know how to care for trees, how to trim them, how to remove trees that were in an undesirable category, and whether or not it was better to treat a sick tree or remove it. The final group of experts were botanists and taxonomists at the university. These experts were skilled at knowing the scientific taxonomy of how trees in one subspecies relate to trees in other subspecies. Medin et al. Employed a sorting task similar to that used by Ch et al. Participants were given cards with 48 tree names typed on them. The researchers used the names rather than pictures in order to avoid any possible bias of surface features. Participants were asked to sort the cards into as many piles as seemed necessary. They were asked to examine their sorting and resort them if they were not sure. All participants were given ample time to complete the sorting task. Participants also gave justifications for the piles they created. Figure 11.5. A summary of different justifications by experts for how they sorted trees in the experiment conducted by Medin et al. Justification by experts for sorting trees. So the taxonomist had a taxonomic justification most of the time and a morphological justification a bit of the time. The maintenance worker had a taxonomic justification most of the time and a morphological and weed. and aesthetic, and the landscaper had a taxonomic justification most of the time, and landscape utility, and aesthetic and size. The key result from the first study is shown in figure 11.5. This shows the different kinds of justifications provided, along with the portion of participants in each expert subgroup that used that type of justification in their sorting. Expert taxonomists used primarily taxonomic information in order to sort the trees, and also used some morphological information. This should be expected because expert taxonomists are experts in taxonomy, and they sort the trees accordingly. The expert maintenance workers, however, provided many more justifications. They used many cases of taxonomy and morphology, but also a sizable number of the maintenance workers' sorting strategies relied on weed trees as a justification, as well as fewer mentions of size, distribution, etc. The landscape architects again relied on taxonomy, but most of their sortings also relied on whether or not trees were considered as weeds. In addition, many landscapers sorted on landscape utility. Medin et al. Interpreted these results as evidence that experts produce and rely on goal-derived categories. The primary goal of tree classification for taxonomists is a taxonomic sort. Maintenance workers also resonate with broad taxonomic differences. Landscapers, on the other hand, intuitively group trees into categories on the basis of how they will be used in a landscape setting. Landscapers may have a salient but idiosyncratic category of weed trees. These might be trees like walnut trees or shrub-like trees, and also have salient idiosyncratic categories that represent different landscape utilities, aesthetic value, etc. Medin et al. Also showed that the three different kinds of experts still retain the same fundamental knowledge about trees, despite these differences in how they sorted. Although they tended to classify and sort the trees on the basis of deep features related to specific goals, when asked to do a categorical induction task, all three groups relied on taxonomic structure. The induction task was similar to the kind of induction tasks we discussed in Chapter 6. Experts were told that a tree of one kind has a novel property, and then were asked which one of two alternative trees was most likely to have that same property. Although the expert taxonomist performed the best in this task, all three groups relied on taxonomy in order to make their inductions. Interestingly, the landscape architects, who had previously shown a heavy reliance on goal-oriented categories like weed and landscape utility, did not rely on these goal-oriented categories to make inductive inferences. The landscape architects were flexible in their classification and conceptual understanding of trees. Their spontaneous grouping reflected their training and goals, but their reasoning reflected their knowledge of tree biology. Flexibility like this is a characteristic of expert thinking. A study by a graduate student in my own lab, Sarah Devantier, demonstrated a similar kind of expertise in medicine. 2009, physicians perform many different tasks during an encounter with a patient. They make a diagnosis, they may prescribe a treatment, and they may manage the patient's health. In many cases, diagnosis and treatment can take a back seat to management. For some conditions, such as diabetes for example, the patient sees their physician to help them manage their disease rather than make a diagnosis. We wondered if expert physicians formed patient management categories that were analogous to the kinds of goal-oriented categories that tree experts formed or that expert physicists might form. We asked a group of endocrinologists, the expert group, medical residents, intermediate group, and med students, novice group, to engage in a forced choice task using hypothetical patient profiles. Figure 11.6 shows an example. Participants in the task were asked to choose which one of two patients was the best match with the target patient profile. One match was a surface feature match, and the other match was a deep feature match based on patient management. At the top of figure 11.6, the one target shows a patient named Mrs. Davis who is 75 and has type 2 diabetes, which she has had for the past 10 years. She lives alone. It mentions retinopathy, blindness, and information about her treatment and medication. Two possible matches are shown below. One possible match is Mr. Harris, who is a 60-year-old widower who has just been diagnosed with diabetes. He has severe crippling arthritis. The other possible match, shown on the right, is Mrs. Martin, who is 74 and has had diabetes for 2 years. The profile also mentions renal failure and retinopathy. Figure 11.6, an example of 3 patient profiles from a paper on medical classification by Devantier et al., 2009. Patient profiles demonstrating surface and deep features. Target: Mrs. Davis is 75 and has had type 2 DM for the past 10 years. She has severe retinopathy and is nearly blind in both eyes. Because she lives alone, she has been unable to check her sugars for the past year. She is currently taking metformin 1,000 milligrams twice daily, as well as gulburide 5 milligrams twice daily. To her knowledge, she has had no hypoglycemic reactions. Possible match 1. Mr. Harris is a 60-year-old type 2 widower with severe crippling rheumatoid arthritis involving the small joints of both hands as well as his knees and feet. He has just been diagnosed with type 2 diabetes based on an elevated fasting glucose and an HbA1c of over 10%. Possible match 2. Mrs. Martin is 74 and has been a type 2 diabetic for the past 8 years. She also has HTN with chronic renal failure and a creatinine of 220 millimoles per liter and mild retinopathy. She used to be on oral hypoglycemics, but because of her renal failure, she has been placed on insulin, which she is tolerating well. Before reading any further, take a moment to look at the 3 profiles in Figure 11.6 and decide which one of the 2 possible matches goes best with the target. Think about why you have made that choice. The target, Mrs. Davis, has several pieces of information that allow for classification into different kinds of categories. For example, the fact that she is 75 years old and female and has had diabetes for 10 years might suggest a category of patient who has been managing the disease for a while. The mention of retinopathy indicates the diabetes is serious. However, another crucial piece of information is that the severe retinopathy has left her blind, and because she lives alone, she is unable to check her own sugar level or administer insulin if needed. An expert who has treated many diabetes patients might recognize this as a crucial aspect to this patient's management. Experts are likely to have an existing category or concept of patients who need home care in order to deal with problems like this. If an expert recognizes these deep features and has a category like this in mind, then the expert might be likely to choose Mr. Harris as the best match and as the most similar. Mr. Harris, although being younger, male, and only recently diagnosed, also has a different condition that would interfere with his ability to check his sugars and administer insulin. He has arthritis. The other possible match, Mrs. Martin, would be a surface feature match because the strong similarities are related to age, gender, and disease history. Although both Mrs. Davis and Mrs. Martin have retinopathy, the impact of the retinopathy differs significantly. Mrs. Martin's retinopathy is mild and does not impair her ability to treat her disease. In other words, Mr. Harris represents a deep feature expert level match, and Mrs. Martin represents a surface feature novice match. We asked participants in each of the groups to view a series of these forced choice classification tasks, choose one of the possible matches, and then provide a justification for their choice. As we predicted, experts and intermediates were significantly more likely to choose the deep feature match when compared to med students. This suggests experts are sensitive to deep feature characteristics and are able to spontaneously group patients into management-like categories. Interestingly, the intermediate participants only showed an expert advantage for forced choice triads, where the deep feature match was related to patient management. On a subset of the forced choice triads, the deep feature match was related to endocrinological aspects of the disease. The only group of experts who were able to perceive this set of deep features were the expert endocrinologists. For this subset of items, intermediates performed equivalently with novices. The implications of this research with respect to expertise suggest that clinical expertise and time with patients is necessary to be able to perceive and use deep feature categories related to patient management. All of the medical students in our sample had studied diabetes and understood the characteristics of the disease, but with no direct clinical experience, they had not acquired the necessary exposure to patients and how to best manage them. The intermediates were in the midst of their medical residency, and as a result had begun to acquire experience in managing patients, but these same intermediates had not taken part in the required fellowship in order to become an endocrinologist. Only the endocrinology experts had enough experience and practice with the biological intricacies of diabetes in order to make the deep feature responses for those trials. Pitfalls of expertise. Most of the effects of expertise on cognition and performance that we have been discussing are about the positive effects of expertise. Experts have been doing their thing, practicing, solving problems, and competing for at least 10 years or more. As a result, they have a rich and extensive memory to use when they are working in their area of expertise. They seem to rely on this extensive memory to fill in the details and retrieve similar solutions so that they can generate a decision or a solution faster and more reliably than most novices can. In a sense, they are using availability and representativeness to their advantage. Because their memories are replete with relevant examples and representations of correctly solved problems, this availability is almost sure to produce the correct solutions. But as with so many other cases in which people rely on what is available in memory, this expert exemplar-driven performance can sometimes generate the wrong solution, and as a result, sometimes experts make mistakes. For example, experts sometimes exhibit inflexibility. That is, if experts are relying on their prior experience, they may be at risk to doing things the way they always did. This can be a pitfall if conditions change unexpectedly. For example, expert accountants can rely on their extensive knowledge of tax law to make sound decisions for their clients, but as tax laws and statutes change, this expertise is not as useful, and in some cases could lead to error. This is what a study by Marchand and colleagues found, 1991. They studied hundreds of tax lawyers. Although experts were usually better than novice advisors, they also found that compared to novices, highly experienced tax practitioners were more likely to rely on previous knowledge than newly acquired knowledge about a similar case. This put them at risk when the new knowledge was needed, and when they recommended solutions for legal cases that were exceptions to the most common tax scenarios, experts made unexpected errors. Marchand et al. Suggest that for many experts, the information retrieval and access was proceduralized, and those procedures did not take the new information into account. Experts rely on memory to their advantage, but there are still pitfalls with that process. Expertise in medical diagnosis. I have touched on the notion of medical expertise at several points in this chapter. Medical expertise is relevant to cognitive processes like memory, decision-making, problem-solving, and classification. This section devotes more attention to this topic. Why focus on medical expertise? There are several reasons. The study of medical expertise is in many ways similar to the study of expertise in other fields. We can discuss medicine as an example that might transfer to other professions, law, business, science, education, and also extrapolate to areas like expertise in games and sports. However, unlike the study of expertise in chess, physics, or even tree experts, medical expertise is the result of fairly standardized training and clinical experience. Medicine carries with it the prospect of great risk when errors are concerned. This is not to diminish the kind of errors that may undermine a successful chess match or a successful landscape plan, but only to emphasize that many psychologists have studied medical thinking and reasoning as a way to reduce the negative consequences of medical error. In most countries, students training to become physicians study for 4 years as undergraduates and then are admitted to medical school. Medical trainees at most schools spend considerable time studying basic anatomy, biochemistry, physiology, and other biomedical fields. Afterwards, students engage in internships and then a residency. The residency is the part of the physician's training that involves the most clinical experience. Although earlier in this chapter we suggested that the so-called 10,000-hour rule is not a hard and fast rule, it should be noted that several years of a residency, combined with time at medical school, is likely to give a young physician close to 10,000 hours of training. Many residency programs involve long shifts and many hours a week. This is necessary because physicians need clinical experience more than anything else to be able to practice medicine effectively. Characteristics of expert medical reasoning. One of the hallmarks of medical reasoning is the degree to which many medical experts rely on similarity and exemplar memory rather than biomedical knowledge or textbook knowledge during a diagnostic encounter. Rather than engaging in specific to general reasoning, that is, mapping the specifics of a patient to the general characteristics of a disease category, many researchers have argued that experienced physicians engage in specific to specific reasoning. 2005. That is, they map the characteristics of a current patient onto remembered exemplars of previous patients. Jeff Norman and Lee Brooks, over the course of many studies, demonstrated that diagnoses by physicians looking at X-rays, dermatological slides, and electrocardiograms rely on specific similarity to previously seen instances more than anything else. Furthermore, they noted that when many of these medical experts made an error, it was likely to be influenced by patient history. They argued that expert physicians do not typically engage in analytic reasoning when making a diagnosis. For Norman and Brooks, analytic reasoning is consistent with System 2 thinking and is consistent with the specific to general diagnostic process. They suggest medical experts generate diagnostic hypotheses on the basis of a comparison of the current patient exemplar with retrieval of highly similar, previously seen cases.